Okay, welcome back. Hope everybody had a good weekend. So today we're going to talk about one of the most important concepts in the entire semester, which is basically how all the machine learning models are trained and the sort of probabilistic or statistical interpretation behind that, which is called maximum likelihood. And then we'll also talk about a generalization called MAP at the end. So the main idea here is that we want to think of machine learning in general as estimating statistical parameters in some probabilistic model. Oh, sorry, what's happening here? Okay. All right. There we go. Sorry about that. Okay. So estimating statistical parameters in some probabilistic model of the data. And this is going to be indispensable as we go forward and we start talking about classification. The least squares kind of heuristic that we've been working with is not going to work. It's not going to be clear what we can do unless we have some sort of probabilistic way of talking about the data. So, so the two best known examples of this are maximum likelihood and maximum a posteriori, or MAP. And so let's just kind of set it up and lay a foundation here. So let's suppose that capital Y is a random variable that depends on some unknown statistical parameters, theta. So for example, you could have a Gaussian Y that depends on a mean and a variance parameter. And so what we learned is that random variable is fully described by its PDF, and we denote the PDF by this small p sub y, and then we have a dummy variable, which here we don't even really need to specify if we talk about the PDF, and we have the statistical parameters, and we're going to put them into a vector theta. And usually when we think about this and visualize this idea in our heads, we plot, we usually plot this density versus y. Okay, so for example, probably the best known example is this Gaussian. So you guys have seen this kind of plot many, many times before, the bell curve, right? And so what we're plotting when we plot the bell curve is we're plotting this PDF versus that argument y. This is like, what is the density at different values of y? And when you make one of these plots, you have to choose the parameters in order to know exactly what density you're talking about. So we chose a mean, mu that was positive, and we chose a variance that gave the bell curve a certain width, right? And so here we're visualizing this PDF versus y for fixed parameters theta. So pretty straightforward. Everybody getting that idea? Okay. And also, because we're going to see it a lot, let's recall the formula for a Gaussian, the PDF formula. It looks like this. So the most important part is that you have an exponentiated negative quadratic. And the width of this quadratic is controlled by this, which is the variance. The center of the quadratic is controlled by the mean. In this thing out front, you can say that the whole purpose of this is a normalization factor that ensures that this whole thing always integrates to 1, okay? So this is just some scale factor to make sure it integrates to 1, but really the interesting thing about the Gaussian is really the exponentiated negative quadratic, and that's what gives it this kind of bell curve shape. Okay, everybody good so far? Okay, so the situation that we actually have when we do machine learning training is not really this situation where we have a single scalar y that we're kind of imagining what y could be. It's kind of the opposite. We are given a whole bunch of y. That's our training data, let's say. And we don't know the theta. We are trying to figure out the right theta that describes that y. So, it's almost like flipped. Here you're saying you know theta, and you're visualizing it for different possibilities of y. And here we're flipping it and saying, no, I actually know y. That's fixed in my problem, but I don't know the theta that I should attribute to that y. Okay, so it's the reverse. So we are going to think of these n different copies of y that we receive, typically our training samples. We're going to think about each of them as an independent realization of the same random variable, capital Y, that is described by this PDF. So that capital Y is described by some parameters theta, which we don't know, and we see many realizations or copies of it. So these are fixed numbers, but we're going to sort of imagine them as samples of respective random variables. And that way we can write a joint distribution. Okay, so this is what we have then. We have a joint distribution across all our random variables, capital YI, but we are fixing their values at the little y's that we collected. And now theta is for us what is unknown, what we're trying to figure out. Okay, so because we have assumed that these y's are statistically independent, this joint distribution across those n capital Y's actually simplifies down to a product of marginal or scalar densities P sub yi, right? So this is the joint over all the different y1 through yn. Here, the individual ones for different i's going from 1 to n. And they all are controlled by the same thetas. And because these yi's all have the same statistics as this kind of reference y without the indices, we can just, for simplification reasons, just rephrase this as P sub y, but then we're plugging in the samples of little y's that we have observed. Okay, so this thing that we're talking about now, this is our vector y. Let me emphasize this. This vector py given theta, this is what we call the likelihood function. But this is what's really important. It's a function of theta, not really y, because y is fixed. So when we want to think about this, we want to think about this as a function of theta because we don't yet know theta. Theta can be many things, or it's many possibilities, but there's one, kind of the best fit to the data, that's the one we're looking for. Okay, so basically this is how we then set up maximum likelihood estimation. What is the theta that maximizes this likelihood function? In other words, what is the most likely theta given that we have observed the data y? Okay, so this is basically the maximum likelihood approach. Is it kind of clear what I'm saying at a high level? This is known. Sorry, this is known. Known data. This is like our hypothesis. There's many possibilities of theta, and we're trying to figure out the best one, which is the one that maximizes the probability that we have observed just that data. Okay, so is everybody with me so far? Because that's basically the super important idea. That is the definition of maximum likelihood. Okay, so now there's reasons that we often write this in a slightly different way, which is arg max over theta of the natural log of that same likelihood. And There's kind of two main reasons. The natural log, so first let me clarify, these are mathematically identical, these two things, because since the natural log function, or any log function, is monotonically increasing, the thing that maximizes log of something is the same thing that maximizes, the original thing. So the value at the maximum is, of course, changed by the log, but the maximizer remains the same whether the log is there or not. The reason we want it there, there's two reasons. One, because this likelihood has a product in it, and that product makes derivations quite difficult. If we take the log of a product, it turns into a sum, and it's much easier to handle. The second idea is that often these probabilities have some kind of exponential in them. Like when we saw the Gaussian, there's this exponential. The log will also cancel that exponential, making our lives once again easy. So this is the reason why we can write maximum likelihood either of these two ways, but this is the way that is often most useful. Everybody good with that? And one more way that we also write it, if we want to turn this into a minimization problem, which is also very popular, we do argmin of negative log of the likelihood. Sorry that I'm running out of space there. And again, these are all equal, but the reason the minimizer is sometimes easier is that often when you take the log, like for example, if you took the log of this Gaussian, what happens is cancels the exponent, and then you get this negative sign. So if you want to minimize this, you can, just cancel that negative and then minimize the result. And that is going to be mathematically a little cleaner. Okay, so these are the different ways that we write the same maximum likelihood problem. Okay, everybody good with that? Okay, so as we'll see, when we do this, when we look for the theta that maximizes the likelihood, we come with no prior assumptions or biases on that theta. For example, if you happen to know that theta should be like very close to 0, that would be like some external knowledge that you want to give to the problem, and maximum likelihood is not going to be able to use that knowledge. The nice thing about this is that sometimes that knowledge can be, people can criticize you. If you're doing science and you have collected data and you want to evaluate your hypothesis on your data, and you put in statistical assumptions, people will say, wait a minute, you already biased the data with your assumptions. Now it's not real science. So sometimes when you do science, you just want to be have no biases. And maximum likelihood just treats theta as completely a deterministic. It can be anything. It can be anything, and just find that theta that maximizes this likelihood. Okay, so that's where we are for the definition. So now this slide just tries to help us visualize a little bit about what's happening. So we have a simple problem here. Tried to simplify it down to something simple as possible. So we have a random variable y, and we know that the variance is 1, but what we don't know is the mean. Okay, so theta, which is usually a vector, is just now the scalar mean. So our likelihood is this, but again, for some fixed y. Or this is actually not our likelihood, sorry. This is just the PDF for a single y. Not yet our likelihood, because our likelihood is going to involve putting in a bunch of y. So, so this is just to recall the definition of the Gaussian, or the form of the Gaussian PDF, when the variance is 1. It simplifies a bit, and it looks like this. Okay. So in this problem, just in this demonstration, let's suppose that we collect 2 samples of data, y1 and y2, and from those 2 samples, we want to figure out what is the mean. What is the maximum likelihood estimate of the mean? What's the most likely mean? So just following the definitions on the previous page, this is our likelihood function. And so we know that what we mean by that likelihood function, it really is a product of py, which has this form, over when we plug in yi for the different i's, and we take the product of those guys. And now we just plug in the equation from above, and this is exactly what the likelihood formula is. So now we want to search among all real numbers mu for the one that maximizes this expression. So to visualize that, here I have examples of this waveform for different mu's. You know, this is if I have a mean of -1, I'm centered here. If I have a mean of 0.2, I'm centered here. And if I have a mean of 1, I'm centered here, right? The red, green, blue. So what we actually have now are we have two samples. And let's suppose that the two samples we have collected are down here, y1 and y2. So what we do is we plug those two samples into this expression. And now that expression is just a function of mu. And so, for example, if mu is -1, the two values of that expression, which we take the product of these two, right? Product of these two heights would be the likelihood. So that height times that height is the likelihood for our hypothesis that mu is -1. Now, there's of course a continuum of an infinite number of mu's we could, hypothesize and look at, but I'm just showing you three examples. If our hypothesis is 0.2, then we get these two values for this, and we're going to take the product of those two heights, those two numbers. And finally, the third hypothesis is mu equals 1, and now I have these two samples, and I'm going to take the product of those two heights. Okay, so if I'm choosing among these three hypotheses, and I want to know the one that maximizes the likelihood, let me ask this to, is Paul Gable here? No, okay. What about Alan Abdelnour? What about Carson Bryce? Yep. So which is going to be, of these three mu's, which is the one that maximizes the likelihood? 0.2, right. And why exactly?
Because the product of the p-values is greater.
Exactly. The product of these guys is the likelihood function, and this is the mu, at least of these three, that gives the highest likelihood. And in fact, if you sort of just look at how I constructed this and imagine what happens is if you move mu a little bit to the left, the values will only decrease, right? So the way to kind of maximize the product of the two is to center this right there. Yes?
Is there intuition behind mu being close to the two samples in this one? Like, you want to pick mu that's close to your samples because then if mu is close, then the sample values are high on the filter.
So yeah, I mean, it all depends on kind of what statistical parameter and how it affects the PDF. So for this kind of symmetric type of PDF, when you're looking for the mean and everything's symmetric, then it's this kind of simple case that you recognize where we're just kind of like looking for something like in the center of all the samples. Yeah. But if I had an asymmetric kind of PDF where things were, maybe like triangle but like flat and then coming down, then it wouldn't work out that way, right? Yeah. So it really just depends on the shape of the PDF and how the parameter affects that shape. And it's very general. You just really don't know what it's going to be. Yeah. Okay, great. Okay, so this is maximum likelihood, just trying to illustrate it from a very simple example of what we're actually doing when we do maximum likelihood. Now, usually we are looking for more than just a single parameter mu. Maybe we're jointly fitting the mean and variance, or maybe, as we'll see in the next example, we're doing linear estimation, and we are trying to jointly fit a bunch of beta parameters. Okay, so are there any questions on this page? Is this kind of making sense? Maximum likelihood idea? Okay, good. All right, so now let's come back to linear regression, which is something we studied back in Unit 2. And there, the whole thing we're trying to do is find the best parameters, beta. And when we did this before, we just had this idea to minimize the sum of the prediction errors squared. But that was not really well justified. I think some of you guys asked me, maybe it was during class, maybe after class, like, why are we looking at the sum of the squares? Why are we choosing that as our error? And that's a great question, because it's not always the right kind of error to use. So what we want to do here is to sort of figure out whether there is a case where this is sensible. And so in order to figure that out, we're going to just imagine a particular probabilistic model. And that is this linear Gaussian model, which is perhaps like the most common model you see in statistics and in machine learning. And it's a simple one. You have that the labels or targets are this feature matrix X times this column vector beta of our parameters. That's, we've been looking at that before, plus error. And now the key thing is that this vector of errors, these are the training errors, are assumed to be independent, zero mean Gaussian with a variance that, turns out the variance is not important here, but we're going to call it sigma squared. And notice that in doing this model, we are assuming standardized data, and that allows us, so we know that the intercept term equals 0, and so we don't even have to model it. We're not using the A matrix, but with the ones column, but just the X matrix, and our beta vector doesn't have beta 0 in it, just beta 1 through beta D. Okay, so this is, if we say like, this is, we kind of assume or suppose that our data satisfies this model. We have this zero mean Gaussian independent noise. Then let's look at what happens when we look at a single sample of this model. So let me ask, is Darren Ayrton here? Yeah, so Darren, how would I write this, but for just yi? I'm just taking the ith row of this expression. Okay, so we have beta vector, and then this xi thing, that's also a vector? Yeah. Okay, now, do I need to add anything else? Plus epsilon. Yes, okay, anything else? Linear algebra? I'd be disappointed if this is how you answer it on an exam. Can I multiply, if I have two column vectors, a transpose, exactly. Okay, right, so this is what we have now. If I extract the ith entry in that equation, the ith row. And so what I'm trying to do here is figure out what is the statistical model for this. Okay, so let's think again. All right, what is random here? The epsilons are random, right? The beta, this is just some set of numbers we're trying to figure out. We are not thinking of that as random. We are also not thinking of xi as random because this is just a bunch of data that we have. These are just numbers we have. And so the only thing that's really random here is these epsilons, okay? And we know that the epsilons are all zero mean sigma squared. So what would the statistical model be for yi? Let me ask this to Sirach Gench? Sirach? Anybody? No? Okay, what about Zach Herman? No. Herman? Zach? Yeah. So if we know that this guy is zero mean Gaussian with a variance of sigma squared, what is this? So let's come back to this picture here. Imagine that I have this distribution, and now I just add an offset to this, maybe a positive offset. It just shifts this, right? So that's kind of what's happening here. I have this zero mean random variable that's Gaussian, and I have a fixed offset. So if this is zero mean and Gaussian, and I just shift it with an offset, the result is still Gaussian, but no longer zero mean. The mean is what? The mean is the shift. This becomes the mean. Okay, so we can write this now as Gaussian. Let me make sure this is what I want to write. Yes, is Gaussian, and yi is going to be kind of the dummy variable that I'm evaluating, and then this has a mean of xi transpose beta, and a variance. The variance hasn't changed at all. It's, sigma squared. Okay, so this is something we're going to see happen over and over again. You have this something with a mean and variance, let's say, some random variable, and then what you do is you just add a constant offset to it. All it does, in most cases, I guess not all, but in most cases, it just shifts the mean. You have to be a little bit careful, and you can always just kind of visualize it. If I have this and I add a constant offset, if I just shift it, what is that new distribution? Okay, so is everybody good with this? Okay, so this is what I have, and this is the density of yi given my feature data and given my hypothesis B. And since these epsilons are independent, the joint distribution of all these y's, which is our likelihood function, is the product of these guys, which is the product of this long expression we saw before. That's this Gaussian. And you can see this is kind of a complicated thing because you have a product of this stuff here. So the nice thing about these exponentials is if I have a product over I of, let's say, exponential AI, then this is going to be exponential of the sum of AI, right? And so what's nice is that product kind of can be slid into, okay, so first let's see, we got to move this out of the product. So that means we have to take it to the nth power. So here we see taken to the nth power. Now this product is here. Now we can move the product inside the exponential by turning it into a sum. Okay, and finally, we've seen that this is just an L2, a squared Euclidean norm, right? We have a sum of squared entries, scalar entries. So here is written as a Euclidean norm. We saw this back in Unit 2. Euclidean norm of y minus x beta. Okay, so this is the likelihood. Likelihood function. And the maximum likelihood estimate is the beta that maximizes that likelihood. So do I have to worry about the denominator? Let me ask this to Alex Rizzoni.
No, everything would be constant, right?
Yeah, exactly. So if I considered the maximum, yes, but if I consider the maximizer, the thing that maximizes this numerator is the same, the beta that maximizes the numerator is the same as the beta that maximizes the whole thing. So I can kind of forget about this from the perspective of maximization. And here you can see we're actually looking at the negative log likelihood because we know we can do that. So that's going to cancel the exponent as well as this minus. And so finally, we're left with this expression. Now, if I want to maximize this over beta, do I have to worry about the 1 over 2 sigma squared? No. So really, the maximizer, or the minimizer, sorry, the maximizer of the likelihood is the minimizer of this quadratic, y minus x beta squared. Okay. And this is exactly what we did back in Unit 2. We just said, let's do least squares minimization. And so now we see, aha, there is a situation where this is sort of a well-founded statistical principle. And that is a situation where your targets are the truth corrupted by independent Gaussian noise. In that case, least squares is the right thing to do, at least from the maximum likelihood perspective. There's a lot of theory about when maximum likelihood is optimal. And usually it requires us, as we collect sort of an infinity of samples, this becomes optimal in various respects. But even for finite samples, you might say it's difficult to argue that it's optimal. It's like the most common thing people do in machine learning is they just say maximum likelihood is a good thing to do. Usually I do have lots of data in machine learning, so that's the situation I'm in. Let's use maximum likelihood. Okay, so that's it. So this is a pretty profound result. if you have this linear Gaussian model with Gaussian noise, then the maximum likelihood is the least squares fit. Is this making sense, or do you have any questions on this? All right, so now, another model that you might suppose is, what if this noise is not Gaussian, but what they call like super Gaussian, which means like once in a while there's a value much larger than you would expect from a Gaussian. So this is what happens when you have outliers in your data, like weird samples that just shouldn't be there. Somehow the data got corrupted. So in that case, this is not a good statistical model for you. And if you apply least squares to this outlier corrupted data, it won't work well. It will fail catastrophically because you are applying a methodology that's sort of well fitted to Gaussian noise on data that does not have Gaussian noise. And so in that case, you might instead come up with a different statistical model, maybe Laplacian. And then you might say, okay, so if my data is ID Laplacian, then what should I be doing? And it turns out, using this exact same derivation, you would end up with the L1 norm. Okay, so that's another very popular thing to do as a method that is robust to outliers. Okay, so all right, so that's kind of maximum likelihood for linear regression. Any questions on this? Okay, great. So now we're going to move on, spend the rest of the lecture on something called map estimation, which goes a little bit further. So this is the case where you have some prior belief on beta. And by belief, we mean this is like a probabilistic belief. So in other words, a prior probability density function. So the way you do map is you solve this problem. What is the most probable betas? And what you mean by that is, what's the beta, most probable betas given my training targets and features? In some sense, this actually sounds like more straightforward, just from it's just saying, what's the most probable betas, right? It sounds like just kind of succinct. The trick with this is you actually need to now have a probability distribution for beta, because here we're treating it as a random variable. Back here, we didn't have any probability. We didn't need a probability distribution for beta. Beta were just like any numbers. Here, it's like a more sophisticated procedure, but it requires more input from the user. And if you say, okay, I have to now assume a certain beta, what if my assumption is wrong? That's where you can get in trouble. If you have a very good assumption, which really does match your data, this can be actually more powerful than least squares. But that's the catch. It can mess you up if your assumption is bad, but it can really help if your assumption is good. Okay, is this idea kind of clear? This is what map is. All right, so now let's see how exactly do you solve this problem. So we're going to use something called Bayes' rule. And Bayes' rule is sort of based on expressing a conditional probability of B given A, as probability A given B times probability of B divided by probability of A. Okay, so I think this is probably something you guys have all seen. It's basically a way to swap the order of the conditioning. B given A, now you're writing it as A given B, and it's now also a function of the marginals, the probability B, probability A. Okay, so this is the main kind of base that we use for Bayes' rule. And so the way that we write Bayes' rule is using that idea. But now, here's the other thing. This X is just going to be some data that we always have. So we're going to kind of sneak in an X at the end conditioning on all these probabilities. And so this is what we get. We get probability of vector Y given vector beta and X times probability of beta given X divided by probability of Y given X. Okay, so I took this idea, but I just conditioned all the terms on X. X, X, X. Okay, so yes?
Sorry, could you give an example of what you mean by a prior belief?
Yes. So in this case, We're talking about beliefs on beta. So as I'll show you soon, what we talked about, last time we talked about lasso and ridge, and they were these regularized least squares regressions, right? And it turns out that that is equivalent, as I'll show you, to assuming you know something about the betas. So if we say the betas are Gaussian with zero mean, and we apply this map principle, you recover what we did with ridge.
Got you.
Okay, or if you say, no, actually the betas were Laplacian, which means they have a peaked heavy tail distribution, then you get lasso. Okay, so it's just like a way of bringing in some prior knowledge about the thing you're estimating. And this shows up everywhere in machine learning, like maybe I'm trying to recover an image from some corrupted measurements. Well, I want to tell my machine learning system, like, I have some belief about what an image is versus what noise is. And so in practice, what that means is you have a giant data set of images. These could be natural images, things on the internet. They could be like medical images if you're working on that. And that becomes your prior. Now the question is, how do I take that and encode it as like a PDF or something? That's another problem. It's kind of complicated, but that's the prior in those problems.
Got you. Okay, that makes a lot more sense now.
Yeah.
Thank you.
Sure. Okay, so this is what we have for Bayes' rule. Are there any questions about how we got here? Okay, now there's one simplification that we can make. When we look at this term, this is the probability of some betas given the features. And notice that that's a little different from this, which is the probability of the betas given both the targets and the features. And the idea is that if I tell you both the targets and the features, you can figure out something about the betas, the prediction coefficient. But if I give you just one or the other, if I give you just the features and no targets, that doesn't tell you anything about beta. It's like you're missing, beta is about how the y's depend on x. So if all you know is x and no y's, basically this is equivalent to probability of beta. So that allows us to make a simplification where we get rid of the x dependent in that last term. So here we have, probability of beta, and then probability of y given x. Okay, so this is what we did. We just simplified this term. And so this now is the thing that we have to know when we do map. We have to have some knowledge or some assumption about the probability distribution of those betas. And here is our map problem. This is the thing we want to maximize. But it turns out that this simplifies. If you think about this, we're trying to find the maximizer beta, but the denominator has no beta in it, so that doesn't affect the maximization. So I can instead look at the arg max beta of just the product of p, y, given beta and x times probability density of beta. Okay, so does anybody recognize this first term here? Py given beta and x? What do we call this? It's what we spent the first half of class on. This is the likelihood. This is the likelihood function. This is the thing, when we do maximum likelihood, we maximize this alone. Right, so this here is maximum likelihood. Forget this. So now we've done map, and we see the difference is we maximize the product of the likelihood and the prior. That is the difference between map and ML. Okay? And likelihood basically says how well beta agrees with our data. And the prior, P beta, says how well beta, this is like a hypothesized beta, agrees with our prior belief about what beta should be. Okay, so these are hypothesized. So we want to do two things here. We want beta to match the data, and we want beta to match our prior belief. When we do maximum likelihood, we only care about how beta matches the data. We have no prior belief. Okay. Is everybody good with map? Okay, so let's see how this connects to regularized linear regression. So this is what we have from the previous page. And just like before, I can put in a minus log if I, instead of it maximizing it, if I minimize the minus log, that's the same thing. This minus this log, you can see, is applied, it's applied to the whole thing. And we also know that log of A times B is log of A plus log of B. So in that case, this product of log of the product is the sum of these two logs. And so here again, we have the maximum likelihood problem, but now we are adding another term onto the negative log likelihood. Okay, so let's come back to our linear Gaussian model, which describes our data. We said that this is IID, the noise, the training prediction, or the training error is zero mean Gaussian. And we said we derived this earlier. If we look at the negative log likelihood, we found out you get 1 over 2 sigma squared times y minus feature matrix times beta norm squared plus some constant. So let me explain that constant. So what we did is we're looking at the negative log of this. So when I take log of, let me put this in red. Log of A over B, I get log of A minus log of B, right? So when I take log of this expression, I get log of the top minus log of the bottom. And the log of the top, or negative log of the top, gets rid of the x minus. And then there's this other constant, which is minus log. Actually, it's minus log of this term. So that's this constant over here. And I'm just writing it as constant, meaning this is a constant in beta, which is the thing I care about. So there's something there. I couldn't leave this out and call it an inequality. There's something there, but it's just not really important what it is, since I care about beta. Okay, so this is what we have for the the negative log likelihood. And so now we are ready to do this. So we're going to have for beta map, we have arg min over beta of 1 over 2 sigma squared norm of y minus x beta squared minus log of probability density of beta. So the reason that I am able to not even write the constant is because now I'm looking at the minimizer. And the minimizer does not depend on the constant. So I don't have to write the constant in there. I still do have an equality. But if I wanted to make this look a little bit more like what we're used to seeing, I can multiply this term here by 2 sigma squared, because that doesn't change the minimizer. And when we do that, we get y minus x beta squared minus 2 sigma squared log, natural log of p beta. And the reason we're writing it this way is because this first term, let's see, is Joshua Joseph here?
Yep, here.
Yeah, so what do we call this? We have a name for this.
Might be wrong, is it L2?
It is an L2 norm, but back before we even really talked about norms, this is kind of our motivation for minimizing this for least squares regression. We minimize the RSS. residual sum of squares. This is RSS is a function of beta. Okay, but now you can see we have something else. And this thing, earlier in this unit, we called this the regularization, and we gave it the name phi of beta. So now, if we lived in a deterministic world like frequentist, sometimes they call in statistics, you just say like, I don't care about probabilities. I just want to minimize RSS plus some penalty. What we've done here is we've explained this in the Bayesian context where we think of things probabilistically. Well, the RSS is this 2 norm, which is a scaled negative log likelihood. And then this penalty term, it's interesting because it depends, number one, on our prior belief about beta. Number two, it also depends on the noise variance. The larger the noise is in our data, the greater we should increase the weighting on this term, or make that term. The larger that term should be. Okay, so basically we see that map under linear Gaussian model is equivalent to regularized linear regression. And so now by coming up with different prior beliefs on beta, we can make different penalty terms. And we can recover ridge and lasso like we saw earlier. Okay, is this making sense? Great. So let's actually just go through those then. So this is what we have from the previous page. This is our map expression. We have RSS and phi. But now let's try to figure out some options for this guy. Log density on beta. So first case, let's assume that each of our beta j's is Gaussian with zero mean and some variance v that we have to, we must assume some assumption for this. So if that's the case, let's take a look at what let's take a look at what the distribution of p beta is. Okay, so we're assuming here that all of the betas are statistically independent and identically distributed, so we're just gonna have a product of a zero mean Gaussian with variance v. So the zero mean, you can see that there's no shift by mu inside the squared, and the variance v shows up in these two terms. So this is what we have for this joint distribution of the different betas. And so that means now if I take the log of this, well, taking the log of this expression, I can move the product into a sum here. I can get rid of this exponent. There's going to be a constant from this term, but for the perspective of beta, it doesn't matter. And so this is the log of beta. Log of probability density of beta. So I plug this into this expression, and this ends up being my regularization term. And now what's interesting is you notice that alpha, which is the scaling on the squared norm, takes a very particular number, sigma squared over v. In other words, like if you really did know the amount of noise in your training samples and you really did have faith that betas were drawn from this distribution, you would not need to do cross-validation for alpha. You would know what alpha is. It's exactly that. But in practice, we might say, okay, this prior pretty much tells us betas should be near zero. They shouldn't be crazy large. And the v that we choose is like, well, how large should they be? I don't know. So, and maybe we also don't really know exactly how much noise is in our data. So we kind of merge those two parameters into this ratio alpha, and we tune that with cross-validation. And then that becomes a super useful thing, especially when the x's are correlated, as we saw, and that's ridge. Okay, so is ridge making sense? All right. The other thing, what if we believe that the betas are ID Laplacian? So let me draw a little picture. So they kind of look like, Laplacian is like a peak distribution. Sorry, I'm not drawing this very well. And its tails are heavier than Gaussians, meaning it allows very large values with higher probability than a Gaussian does. So basically this says, okay, on average, your betas, they're zero, but like they could be pretty large once in a while. And how large they are is going to be determined by this scale factor lambda. So this is the distribution of a Laplacian. Looks a lot like Gaussian, but you can see it's missing the square root in the denominator, and it is missing the 2 here, but most importantly, instead of a square, it has an absolute value. So that's where you got this peaked shape. So when you look at the log of this, the product goes into inside the exponent as a sum, and then that becomes an L1 norm scaled by 1 over lambda, and this turns into a constant once you take the log. Not very important because we are just trying to optimize over beta. So finally, we get this, and this now tells us that this is lasso with a very particular parameter for alpha. Alpha is 2 sigma squared over lambda. So again, if you really knew your betas behaved this way and you knew your noise variance in y, you wouldn't have to do cross-validation for lambda. You would just automatically know what that should be. Okay. All right, so that pretty much concludes map. Any questions? All right, so let's briefly just pause and review what we saw since it's so important. So we're saying supervised machine learning can be framed as statistical parameter estimation, parameter being the thetas, and statistical meaning we have some model of like probability y given x and beta, or maybe even probability of beta. So we're now saying we have to have these things to use this kind of technique, but this is how we can frame all machine learning problems. And we looked at 2 versions of this: maximum likelihood, which is find the thetas that maximize py given x and theta. And we looked at map, which is maximize p theta given y and x. Okay. All right, so that concludes this thing, and we're going to be basically relying on ML for the rest of the term. So super important stuff, and this kind of material is perfect for midterms. All these like probability distributions and deriving, minimizing or maximizing this. We can do this with calculus, right? You figure out where the slope goes to 0, just like we did back in Unit 2 when deriving the least square stuff. So lots of good opportunities for midterm questions. And there's one more thing I want to talk about just briefly, since it relates to the lab that is due this Friday. And it has to do with linear regression with multiple targets. So until now, we haven't really talked about this. When we do linear regression, we have multiple beta coefficients, right? But we have a single scalar y we're trying to predict. So what we're saying is actually there's cases where you're trying to predict several different things at once, several different targets at once. So we're going to think of the different targets. We're going to introduce a new variable k. K targets. So our targets, we can think about them as having components 1 through k, or we can just think about them as a vector, a k length vector. And it usually makes sense to think about to have this as a row vector, so transposed boldface yi. And so this is the model that we saw before. If we think about what happens at the ith training sample, the linear model says yi is approximately equal to 1 times the beta 0 coefficient plus xi transpose, or inner product between xi and all the remaining beta coefficients, right? So that's what we had when we had a single scalar valued target. And now we're often going to consider cases where we're trying to predict multiple things at a time, k things at a time. So instead of a scalar yi, we just have a row vector. This is the same. We just have the same features to do our prediction. But now instead of one column vector, we stack a bunch of column vectors into this matrix. One prediction vector beta for each target. So in other words, This beta 1 is being used with our features to predict the first component of the target vector. The next beta 2 predicts the next y. The last one predicts the last y. They all use the same features for prediction. Is this making sense? Okay, so this is what you're going to see in the lab. So basically, like everything is the same that we saw before. We want to find the betas that minimize least squares prediction error, or you could say maximize the likelihood. But now it's just like you simultaneously solve for k different beta vectors. So conceptually, it's not a huge change. And we're just now calling all those beta vectors together the B matrix. Okay, so this is what the overall model looks like. Each one of these is the data for a new component that you're trying to estimate, or you can think about the rows as being data samples. Here's all our k predictors. So this is, you could say the model is now vector y approximately equal to A, same matrix as before, times B. Okay, so this is what we do when we have multiple targets to predict simultaneously. Just use multiple prediction vectors. Okay, any questions on that? Okay, so what happens to ridge? The first thing that happens is, since we're using matrices and not column vectors, and we want to do sum of squares, it turns out that if you would just put in the regular L2 norm, the L2 norm on a matrix is not the thing we're used to. It is not sum of squares. It has to do with the singular value decomposition and stuff. So instead, we have to just change our notation to the Frobenius norm, the matrix Frobenius norm. This is just the sum of the squares of all the elements in that matrix. Okay, so this is for ridge. This is what we would have. We have a Frobenius norm in those two places. Meanwhile, for lasso, we have the Frobenius norm in the first term, but it turns out the L1 norm for matrices is the same as it is for vectors. So we can still use the L1 norm there, matrix L1 norm. Okay, and the last thing I want to say is that when you're doing scikit-learn linear regression, everything works with matrices. You don't have to tell it that you're using matrices, you just give it matrices and it does all the right things. It solves for those betas. Sorry, yeah, the betas are the B matrix. Okay. There's also ridge and lasso methods, as you know. It works with matrix data there too. No change to the code at all. Okay, so that's it. Any questions on this last part? Okay, great. So this will be useful for your labs. And then next time we will start the next unit where we will shift to classification. So we're done with regression. See you guys on Wednesday.